This will be a little bit more of a conceptual video. We'll definitely have plenty of time to think about working explicit problems, but I wanted to introduce the idea of similarity theorems by being a little more general, and that the idea is, do angles determine shapes? That's the slogan. More explicitly, if I know every single angle in a polygon, does that completely determine its shape? Or is there some way I could stretch it or bend it or make it floppy or something so that I get two genuinely different shapes that have the same angles? And we know that that same shape, the explicit word for that is similarity, but let's just look at it in the intuitive level. So here's probably the simplest example. I asked GeoGebra to make me a shape with all four of these angles being right angles. So it is a rectangle. It happens to have a very particular shape. It happens to be at least very close to being a square. And the question is there some way I could stretch it or reshape it so that it's no longer exactly the same shape? So in particular, it's no longer a square, but it still has the same angles. Well, we know that there are non-square rectangles. And the great thing about GeoGebra is I can kind of do that explicitly. I can just take this and drag it, and clearly those angles, none of those are changing. They are all still right angles, but that's a long, skinny rectangle. That's a wide, fat one, not very tall, and that's about back to square. And you can see I've got these dotted lines. I've made rays here as kind of rails, kind of tracks that I can slide this thing. It's like a trombone, I guess. And so clearly, no. The answer is just no in general. You can totally have two shapes that have the same angles, or really you're not the same shape. And they're certainly not similar in the more technical sense. Now, what about if they weren't right angles? I had to think about this for a second. What if I had something where I made sure that this angle at A is 50 degrees, the angle at B is 120 degrees, and that determined these two rays here. And then I additionally said the angle here, I made sure it had to be 100 degrees, so it kind of turns in a certain way. If I'm going up here, it turns a certain amount, 100 degrees, and heads off over towards this other rail, and intersects at J. Was it kind of really special with that sort of right angle parallel rays thing? Well, no, because I can, again, just take this guy and I can totally do the trombone thing, but it's going to be just looks a little more complicated. But notice the angles don't change. The 50 and the 120 are just totally locked in. They determine what these rails look like that I'm sliding E on. I locked in this 100-degree angle, and GeoGebra is good at just keeping that at 100 degrees. And this angle has to be 90. If you want to think about that for a second, I think I'll do a little quiz. The reason that had to be 90 is that the angles in a quadrilateral, we know that those have to add up to 360. And so this is 170, 270. Okay, that had to be 90. And so I didn't have to specify to GeoGebra, okay, make sure to keep that 90. It's automatic, and it's just calculating that 90, not creating it. But in any case, these are quite different shapes. I can still make it long and skinny, still make it kind of short and kind of clunky and chunky. And so for quadrilaterals, angles absolutely don't determine shape. So that might be just bad news. Like, oh, it would have been nice to have some theorem that says as long as you check the angles are corresponding in two polygons, that they will have the same shape. In other words, that they'll be similar. But that's just not true for general polygons. So that's why when we look at general polygons in section 7.2, it's pretty laborious. We have to check all the angles correspond or congruent, and all the side lengths are proportional. If we just checked congruence of angles, we could mistakenly say this is similar to this, and they're not the same shape at all. But the key is for 7.3 is that triangles are very different, right? So let me pull this over, right? Do angles determine shapes? And so what we see is that the answer to that is no. for general polygons. And the claim is yes for triangles. Triangles are incredibly special. We already know that from last semester from the triangle congruence theorems. And then this is the corresponding thing. So I'm going to do this live in front of you. I'm going to take, let's say, I will actually get it to create an angle at C here. Let's say with, I think I wanted a 50-degree angle here. Okay. And it gives me a point. I don't really want a point, so I'm just going to quickly turn that into a ray. And I'm actually going to hide that point because I don't want to be forced to use that point. The main thing is I want to just create this ray. So that's just a ray going off at a 50-degree angle. Now I'll do the same thing over here at D. Let's say 75. So I think I want to do. Ooh, and I want it to go the other way. Otherwise, it turns out to go downward. Okay. And I'm going to make a ray again. Okay. Now, okay. So I've got a baseline segment. Now, I haven't talked much about the length of the segment, but it happens to be 3. I chose that to be 3. And so I have this 3 base, and then I said, I'm going to make some sort of shape that where it's got a side that's going off at a 50-degree angle to the base here at C, and it's going to going off at a 75-degree angle here. I think you can see that now better. And so notice what happens. These 2 rays, they have to intersect at exactly this point. There is one and only one point where those intersect. And I will go ahead and actually label that. There we go. And it's calling it N. Okay. And so there's no choice about what this triangle has to be. And this is the ASA situation that you know from congruence theorems, that if I specifically know this length is 3, and I know this length, this angle is 50, and this angle is 75, there is no choice as to what the rest of the triangle looks like. These 2 rays intersect in one point, and that point is completely determined. And so in particular, I can I can figure out how long this side CN is. There's no ambiguity. It turns out, in this case, it turns out to have to be 3.54. And what about D to N? Oops. Let's measure again. D to N has to be 2.81. And that is really a review of the ASA congruence theorem, that if I have ASA data about a triangle, there's no ambiguity. This couldn't be anything but 3.54. This couldn't be anything but 2.81. Now, exactly how you would calculate those numbers, that's something we don't yet know how to do. But the theorems you already have say that there isn't some other triangle with this being 3, this being 50, this being 75, and this being 4.92. That's just not possible. And so what I would like to say is that triangles are rigid. Triangles are not floppy. Triangles, you get the angle data here, and it determines everything else, where that point is, what these 2 sides are. What does that say about similarity? Let me bring this guy into the picture. I went ahead and pre-made a triangle that had exactly the same base angles, 50 and 75, and I just made sure that the base side length was exactly twice as much. What do we expect? We've got all the angles are the same. Notice that I didn't measure this angle yet. I should go ahead and do that. Let's just make sure we know that it's kind of annoying I can't click here. Let me, yeah. Okay, now it's measured. It's gone ahead and confirmed, as it has to be, that that's 55 degrees. If you add those up, you'll see those do add up to 180. And this has to be 55 degrees as well. So if I know these 2 angles, I really know all the angles in this triangle. And then I know this one side is 3. If I see a triangle with all the angles matching, I claim that it has to be the same exact shape. Technically, that means it's similar. And then if I notice, oh, these 2 corresponding sides are in a 2-to-1 ratio, I should be able to conclude that that's a universal scale factor, that this triangle is really exactly what I would get by just blowing up this triangle by a factor of 2. Let's just check that real quick and end the video. Let's go ahead and see. What is Km? Oh, 3.54, you double that, you sure as heck get 7.08. And 2.81, you double that, you get 5.6. Ooh, looks like there's a rounding thing. It should be 5.62, but maybe this was a little off too. But you can see it's going to be double. So that's our fundamental similarity theorem, that if I have two angles matching, I obviously get the third from sum to 180. And then whatever the proportionality that I see in any particular pair of sides, I'm guaranteed to get the same ratio, that same scale ratio in the other sides.